try to do. Yeah, I'll try to motivate why these Higgs doublet models, in particular Higgs doublet models, are important. I'll talk about the symmetry constraint, and then I'll review some topics which are the unitarity and bound from below conditions, paying special attention to sufficient bound from below conditions that we have derived for some of these models. Then I'll turn to a new type of fermion coupling, which is present for the first time in 3Higgs doublet model, the so-called type Z. And in the second part, I'll move on to another symmetry A4 3HDM. I'll study both the symmetric and softly broken case, looking at the vacuum and trying to fit the quark mass matrices. And in the end, showing that softly broken A4 can produce a good fit of this. Okay, then starting from the beginning, well, the first question is why only one Higgs boson? Well, we know that in gauge theories, once you fix the gauge group, you know how many particles you have from spin 1. As for the number of particles of spin 1/2, there is no principle. Then in principle is fixed by experiment. Essentially, the number of generations was fixed by lab. And of course, LHC is trying to confirm that, but if there is a possibility of a heavier generation, but now it seems unlikely. And but it's an experimental question. And for the number of spin 0 particles, also there is no principle, and it should also be fixed by experiment. That's the idea. Can one determine the number of scalars? Well, in general, no. Why? Because many of these theories have decoupling limit, and in the decoupling limit, the heavier Higgs will escape detection. Then it will be difficult to know exactly how many. In fact, we have proved the theorem that says that an HDM with a symmetry will exhibit decoupling only and only if the vacuum satisfies the same symmetry. Can give us a quick example. For instance, if we take n equal 2, we have the exact Z2 HDM. We have a VEV in the first entry, then it respects the symmetry. Then this model is known as the IDM model, inert doublet model, and it has a decoupling limit. For instance, if you now take the exact Z2 symmetry with 2 VEVs, as this does not respect the symmetry, we have no decoupling. But of course, you can fix this by adding a softly broken softly broken the theory, adding a M12 term, and then you have a decoupling limit. Well, although in general you cannot count the number of scalars, sometimes yes. For instance, you can be lucky. You can detect some of the X's at LHC, or direct or indirectly through loops where they contribute to some visible process. Then it's a question that we have to be open and see what the LHC and future colliders have to tell us. Now, next, why 3HDM? With well, there's been lots of activity in this type of models. They have extra sources of CP violation. They can add new dark matter candidates. Then they contribute to solve some of the questions of the standard model. The scalar potential for the most general 3HDM can be written in this complicated or compact, better form. And if you count the independent parameters, you have 46, from which 30 are magnitudes and 16 phases. And of course, this is far too many to be able to do any phenomenology with these models. Then what people do, essentially, they try to reduce this number by constraining the model by imposing symmetries on the Higgs potential. And that's why I'm talking about this symmetry constraint THDA. Then the full list the symmetry constraint HDM was given by Ivanov and Vlovdin, and they gave both the discrete symmetries and the continuous symmetries. Then you have a finite number. They are quite, I mean, they are not one or two, but they are finite, the number of these symmetries. And then you can try to use some of these to constrain your model to reduce the number of parameters. And in the rest of the talk, that's essentially what I'll be doing. I'll choose some of these discrete symmetries and try to see what are the consequences of that. The other thing about 3HDM is, sorry, especially in a way that I wanted to tell you. Well, we have in nature 3 types of fermions with different charges. They are quarks, down quarks, and charged leptons. And to avoid flavor change in neutral currents, we need to couple each of the fermion types to at most 1 Higgs doublets. In 2 Higgs doublet models, it is well known that we have 4 possibilities that nowadays people tend to call 1, 2, X, and Y. Sometimes also lepton specific are flipped instead of X and Y. But if we, with n equal 3, with 3 Higgs doublet model, we have a new possibility in which each fermion type couples to a different Higgs doublet, and this is called type Z. And this is special about this new possibility, because if you go to n bigger or equal to 4, as we have only 3 type of fermions, you cannot have any new thing. I mean, you can have 1, 2, X, Y, and Z, but not any different type of coupling. That's why the 3HDM is the first time that this new coupling appears, and it has not been much studied. That's one of the interests of this type of models. Now, we want to implement, we have implemented many of these models numerically with the numerical codes that will generate points in parameter space, and then we'll try to look at the observables that can be measured at LHC to confront. And but to have a consistent model, we have to look first at what are the theoretical constraints on the model. And the first one that we consider is, of course, perturbative unitarity is a theoretical requirement in any reasonable beyond standard model theory. And this is done by requiring that the eigenvalues of the 2 to 2 sketching amplitudes of the scalar fields be bounded as results from the optical theorem. And this is well known for simple cases like the standard model, almost trivial, and 2HDM. But for larger n, although things are known in principle, we proposed a few years ago with Aber and João Silva and Bento, an algorithm to find the relevant sketching matrix. Then we have an algorithm. Then for any NHDM, we can produce an algorithm to find the relevant sketching matrices. Some, of course, they can be quite large. Recently, we have explicitly evaluated the sketching matrices for all the symmetry constraint 3HDM that were shown in the table and discovered by Ivanov before. Sometimes when you do this, you have large, then the idea is that you have to find the eigenvalues of these sketching amplitudes, and you bound them by 8 pi. That's essentially what comes from the optical theorem. But sometimes these sketching matrices are very large, then you have to numerically diagonalize them, and sometimes you have numerical problems. And to avoid that, you propose them a method of enforcing this unitarity based on principal minors, which are easier to deal with than finding numerically the eigenvalues. And This is explained in this paper with Bendo and João Silva. And it turns out it can make things much stable and faster. Now, the second theoretical point is bounded from below. Then any good theory for beyond standard model must obey bounded from below conditions, not only along neutral directions, but also along charge breaking ones. And sometimes people kind of forget about this last part of the bounded from below conditions. Now, the necessary and sufficient conditions are trivially known for the standard model and also well known for the 2HDM. But for a general 3HDM, no such conditions exist. They are only known for the case of some symmetry constrained 3HDM like U1 cross U1 or U1 cross Z2, but for instance, the Weinberg model Z2 cross Z2, they are not known, neither they are known for the Z3 symmetric model. Why are they not known? Because this...
Excuse me, I have a question.
Yeah.
When you're talking about bounded from below, you're talking about the scalar potential? I mean,
yeah, the scalar potential, yes. Okay. And the difficulty is that these potentials, they are very complicated if you take 3x, and it is very difficult to look at all directions. Ivanov has developed some clever methods to do that, but the general case is not treated, or even the simpler cases like Z2 cross Z2 or Z3. Now, to circumvent this problem, we have implemented a more restrictive sufficient conditions that allows us to be sure that our points in parameter space are all okay, although by being sufficient, we can be throwing away some of the relevant parameter space. And for instance, we also did this for these two cases where the necessary and sufficient conditions are known. And we compared the data sets with the sufficient and necessary and sufficient conditions with the data set just only with the sufficient. And for some observables, we didn't find any difference between the two data sets. But of course, this is because we just look at a few. We are not sure that some difference might appear. Now, how can you get sufficient conditions? That's much easier than necessary and sufficient conditions. And I'll explain what is the idea. Now, you want to look at the quartic part of the potential, which I write in a rephasing invariant part plus some part which belongs to the group. Then we are considering here 4 different cases: U1 cross U1, U1 cross Z2, Z2 cross Z2, and Z3. As I told you before, for these 2 cases, the necessary and sufficient conditions are known, not for those ones. Now you have this rephasing invariant part, and then you have the part that corresponds to the group. And for U1 cross U1, it's just 0. And for the other, it depends on some extra parameters below, more or above these 9 parameters that enter this part of the potential. Then what you do to analyze these sufficient conditions? Well, first we start looking at this rephasing invariant part. Here I'm following very much the procedure of Igor Ivanov. I split this in 2 parts: the neutral and charge breaking. I'll come in a moment why these are called neutral and charge breaking, and I write them in this way. And to write the charge breaking, I use this trick of kind of substituting these quartic terms that appear in the potential by this rule, and writing them in terms of this Zij. Well, notice that comparing with the previous potential, which has 9 parameters, this also here you also have 9 parameters, but we have renamed the coefficients for convenience. Now we define our fields using SU2 cross U1 invariance. You can redefine the fields into this form, the names neutral and charge breaking come from when you substitute this expression for the fields in this potential. The first part does not depend on alpha 2 and alpha 3, which means that they don't depend on the charge breaking directions. That's why we call it neutral, while the VCB depends on alpha 2 and alpha 3, then they are along these charge breaking directions. One important thing for what follows is that these Zij are bounded. In fact, they are bigger than 0, and they are bounded by the product Rij, where R are these coefficients of the three doublets. Now, with this, we first look at the neutral part of the potential. Then this has a quadratic form in Ri and Rj with this matrix. And it is well known that for this quadratic form to be positive for Ri bigger or equal to 0, you have to impose compositivity conditions, which, for instance, in the form that were proposed by Kanike, have this can be written that way, essentially, where these A, I, J are the entries of this matrix. Then, if you know what is the matrix, and then you apply these conditions, and if they are all satisfied, then this ensures that the neutral part of the quartic potential is bounded from below, and these are necessary and sufficient conditions. Now, for the VCB part, Ivanov and Faro also found the necessary and sufficient conditions using geometrical methods. The result is a bit complicated, but we are not going to that direction because we don't know how to do it for all the other symmetry constraint models, but you want to find sufficient conditions also for the VCB part. Then what we do, now the idea is that you bound your potential by a lower one that can be written as a quadratic form so that you can use the compositivity conditions. Now, if you remember that these Zij are bounded, you can say that the VCB is bigger or equal to some lower, and this lower is the product of this R1, R2, and so on, with the minimum of the between 0 or these coefficients that were in this expression. Okay. Now, with this, now you just now you have this quartic part, which is the sum of the neutral part and the charge breaking, and you bound it by this expression, by this potential. And essentially what you have to do, you redefine these matrices with these conditions that come from there, and now you have this matrix, and you just require that this matrix corresponds to a positive quadratic form, and this will ensure sufficient conditions. They are not necessary because we are bounding it by a lower one, not really equating it to another potential. Now, next, the last part is now we have to look at the group, at the symmetry, at the part that comes from the symmetry constraint part of the potential. And as I told you, we had 4 cases. Then for the U1 cross U1, as this is 0, you don't have to do anything. Then if you already bounded it by Vn plus VCB, it's done. For U1 cross Z2, you can bound it by this kind of term, which again as a product of R2 and R3, which means that you have to redefine the 2, 3 entry in the matrix by this expression. You to this one that we had before, now you have to add this one. And for Z2 cross Z2, you do a similar thing. Now you have let me perhaps go back. For you have these terms, then you substitute the phi's, then you write an expression in terms of R1, R2, and R3, and it turns out that the expression is this one, and now you get a lower bound for Z2 cross Z2, and using this, essentially what you have to do is just to redefine the elements of the matrix. Now it gets with more terms, and then you just require compositivity, and you know that you have sufficient conditions. The more complicated case from all these four is Z3. In Z3, you do the same thing, but now once you substitute the phi I by the expressions that I was giving before, essentially two things happen. First, there are some functions here that depend on alpha I and beta I, which was not the case before. That's the first thing. And the second is that instead of having a product of Ri, Rj, you have square roots there. And of course, it's not in the form of a quadratic form, then you have to take care of both problems. For the first problem, we are lucky because you can show that this F1, F2, and F3, they are bounded. In fact, the absolute value is smaller than 1. And that's, of course, very convenient for our purposes, because you can do a first step, you bound this potentially by this one, which now, of course, has no more the angles alpha I, beta I, and gamma, but as the square roots. For the square roots, you use a trick. You can show that if Ri is bigger than 0, as they are, minus square root of Ri times square root of Ji, which are the terms that appear there, are bigger than minus Ri Rj. Then you plug it in there, and you get that you bound it by this expression, and now you rearrange terms to be in terms of the products of R1, R2, R1, R3, and R2, R3. And then essentially what we have to do is just to redefine the entries of your matrix in your quadratic form, and you require compositivity, and that ensures that you have sufficient boundary conditions for all these four potentials. Of course, they are sufficient, they are not necessary, and they cut more perimeter space than the necessary and sufficient conditions. Although, as I've told you already, for these two cases where the necessary and sufficient conditions are also known, we checked, for instance, you look at signal strengths, and did not find any relevant difference between the two data sets, the ones with sufficient conditions and the one with necessary and sufficient conditions. Then, of course, this is not a proof. This is just an indication that perhaps it's not too bad just to consider sufficient conditions. But the problem is that if you don't know how to have necessary and sufficient conditions, it is better to use sufficiency, because if you use sufficiency, you are safe. Although you might throw away some physics that you don't know yet. Now, this is for these theoretical constraints. Now, let's come to the type Z coupling. We are interested in the possibility of this type Z Yukawa structure that requires a 3HDM. And there are at least two different ways to ensure this structure. One employs Z3 symmetry, and the other Z2 cross Z2 symmetry. And this is the way the symmetry is implemented. And if you look at Yukawa terms, both of these symmetries will give rise to the same type Z Yukawa couplings, so that these two models, Z3 and Z2 cross Z2 prime, will not be distinguished by the Yukawa sectors. But of course, as I've told you before, they have different structure in the Higgs potential, And we will try to see if it is possible to distinguish them just by looking at something which is related to the Higgs potential. Now, but now I'm writing again this potential. Now I'm including something that I was not giving explicitly, a quadratic part of the potential. I was not giving it explicitly because I was just interested in bounding from below conditions that come from the quartic part. But normally you need not only these terms, but you normally also put some softly break terms, and because that helps having heavy scalars without spoiling perturbative unitarity, and that's normally what you do when you look at the phonology of these models. Now, the differences that we are looking at will come from the quartic terms, which for these two cases have these expressions that I've already shown you before. And we therefore hope to find some distinguishing aspects of these models by checking the effects of these additional terms. For this, we have to implement the model, then we have to make a scan, and you have to choose what are your parameters, and we took as parameters as many as physical parameters as possible. And of course, I'm considering physical parameters the masses of the scalars which have not been yet discovered, but that's what normally people do. And of course, I'm taking the one which has been seen as 125, and then we have two extra scalars, two pseudoscalars, and two charge X in this type of models. You need also some mixing angles. You need this alpha I to diagonalize the scalar mass matrix. You need beta I to rotate to the charge spaces, and gamma I to diagonalize the pseudoscalar and the charge spaces once you go to the charge spaces. You also need finally the softly broken masses, these parameters that I was putting there. And with this, and you can invert using minimization equations and expressions for the mass matrices. You can invert for all the coefficients that you have in this, all the lambdas can be written in terms of these parameters, and that's normally the most convenient thing to do. In our parameterization, we take the VEV to be given by the double mass, of course, and the relation between the V1, V2, and V3, and the VEV is given by this beta 1 and beta 2. Now, what you do for the scan? Well, in principle, we like to have a general scan, which means that you take the angles between minus pi over 2 and pi. You take tangent beta, you don't take from 0 because of some results on B physics, up to 10, or even, I mean, there is no reason to stop at 10, but it turns out that higher values of tangent beta are very fine-tuned. You take the masses up to 1 TeV, and for the soft terms, these are every dimension of mass squared. You take between, they can be either positive or negative, and you take between minus 10 to the 7 and plus 10 to the 7. However, if you do that, you will find out that once you impose all your constraints, the scan produces very, very few points. For instance, for Z3, with the latest LHC data from Atlas, you get 1.4 out of 10 to the 10 random points. It's really very, very, very low. And Das and collaborators just noticed this, and they showed that in order to generate a fair amount of good points, you should not be far away from what they call the maximally symmetric limit of the GHDM. And this is defined by these equalities where alpha 1 is equal to beta 1, alpha 2 to beta 2, and some relation between gamma 1 and gamma 2 and alpha 3. And the masses are equal in two pairs. The one of the scalars, it goes to with the pseudo-scalar and one of the charge x's, and the same for the second set. And on top of that, you also need to have some precise relation for the soft masses, which in this limit are no more free parameters. They can be determined from the minimization conditions. What is special about this limit? Well, for one thing, of course, many of the parameters are disappearing, and that, of course, makes things makes life simpler. But the reason behind this is a good limit is because you can show that in this maximally symmetric limit, the potential is just given by this very simple form, where this is the coupling constant of the standard model, which is well known. And then automatically you satisfy perturbative unitarity, you satisfy bounding from below, you satisfy STU, and so on. Then you are probably, because of this is mostly like the standard model, you are satisfying also the LHC constraints on the mu's and the many constraints. And in this limit, essentially all the points are good. But of course, this is, although this is good because you have lots of points, they are not very interesting in the sense that in this limit, the couplings of the small h, the standard model like X, are exactly like those in the standard model. So you don't have much for BSM physics. And if you want to have some new results to depart from the standard model, you need also to depart from this maximally symmetric condition. And of course, you chose to depart from it in a kind of a systematic way. You can be, let's say, 10% away, 20%, 50%, and so on. And we have look at those limits. Then, in some sense, we know that we have enough points to do our scans and our analysis. But we are not exactly at the symmetric limit, and you can have physics beyond the standard model. Now to apply this to the codes, you need first to apply these constraints. Then you take the unitarity, as I told you, you can use expressions of our paper for the bounding from below conditions that these two models, they are not known the necessary and sufficient conditions, then you just use the sufficient conditions that I've explained before. The experimental, you use the STU constraints, you take the expressions from the paper well known by Gribus. The signal strengths, you take the latest results from Atlas, and for the other X, you use the X-bound software to discard points which do not fit the LHC data. Now, you want to discover if there is any observable that can distinguish between these two implementations of type Z in the GHDM. And then the first thing we thought was just look at the signal strengths, because they are very well measured by now at LHC. But if you look at the result, they are very similar for both implementations. In red, I have Z3, and in green, Z2 cross Z2, and the plots essentially are on top of each other, which means that you don't have any feature. Here I'm plotting the mu with the final state gamma gamma and the final state Z gamma, and but this is similar also for the channels. I mean, we have plotted every channel against every channel, and you did not find any difference in these plots, which means that you cannot really distinguish these two cases of the type Z implementation. And if you think a little bit about it, that was more or less kind of expected, because for this type of observable, essentially it is the UCAV Lagrangian that normally it is more important, and of course they have the same type of UCAV, then you cannot distinguish from there. Now, the next observable that we thought it was a good observable was it's called the kappa H, which is defined as the ratio of the triple X coupling in our model with respect to the standard model. In the standard model, it is well known. The lambda, the standard model is also known once you know the mass of the W and the mass of the VEV and the mass of the X. And this is a particular nice observable because it's something that the upgraded experiments at LHC and future colliders will search. Then if you can look at this expression and find some difference, that will be something to look at in the future at LHC. Now, for instance, for the Z2 cross Z2, you can write this expression. Of course, it's not as simple as in the standard model, but it depends on many couplings and the rotational matrices and the VEVs. But you can look if you at the symmetric limit to see if it is in principle at the symmetric limit this should be equal to the standard model. Then you should have kappa H equal to 1, and you can check that because in the symmetric limit you have this relation for the couplings. All the other lambda I for I bigger than 7 vanishing. Then in the end, this collapses to this, and now we use the rotation, the properties of the orthogonal matrix R and the definition of the VEVs, and essentially this just collapses to the standard model value, which means that you have kappa H equal to 1. For Z3, it is the same, because although this expression now differs on these three couplings, as in the symmetric limit, all these couplings are equal to zero for I bigger or equal to 7. Essentially, the two expressions coincide in this limit, and then you also have kappa H equal to 1. Now, you want to see if you can get any difference, and of course, the difference should come from terms in VG, in particular the lambda 10, 11, and 12 terms. And then you plot this for both for Z3 in red and Z2 cross Z2 in green. We plot the kappa H against these lambdas 10 and 12. Well, you could also have plot against lambda 11, which just shows two of them for lack of space. And essentially what you see is that indeed there is a difference between the two cases, which was not present in the single strands. And there is a much larger range of variation for Z2 cross Z2 than for Z3. And essentially also, and that's very important, you can get much lower values for kappa H in the Z2 cross Z3 comparing with Z3. And the other striking thing from these plots is that this kappa H is lower than 1. I mean, this should not necessarily be like that. I mean, this is a consequences of the being close to a consequence of the fact that the LHC forces us to be close to this alignment limit, and somehow we are investigating that more carefully now. But this is something that comes from this from these plots that we also have done for other lambdas. We also have done, to illustrate this, we chose some benchmark points. Benchmark 1 with relatively small masses, a benchmark 2 with intermediate masses, and a benchmark 3 with heavier scalars. And in this heat map plots, we plotted on the left Z2 cross Z2 and on the right Z3. And you see from this scale that green is lower values for the kappa H, and yellow is close to 1. And for these two, for lower mass, it's not so much difference. But if you go to heavier masses, for instance, for this plot here, you don't have any green, and here you have green, which means that you can get to lower values of kappa H in Z2 cross Z2, with respect to Z3, as it was also clear in these plots here. Then we claim that once this the cap age is measured, if it is if it is bigger than 1, then these models will be in trouble to explain because they give a value which is lower than 1. If it is much lower than 1, then Z2 cross Z2 is in better shape to explain the results than Z3. Now let's, in the time left, let's move to another topic related but different. We consider this 3HDM model with a symmetry A4. If the symmetric case, the potential is given by this expression. This is one. I mean, there are other ways of writing the potential, but this is one of them. And the thing we want to focus is that Ivanov and collaborators, they have shown that this potential has only 5 different vacua. I mean, and they are of this form, the just first entry, all entries, just here a complex one and 0, and then these two, they have this eta, which is this complex number, rotation by 60 or 120, and these are the only possible vacua of this symmetric A4. And this angle that I was mentioning is given in terms of the parameters of the potential. For each of these 5 vacua, we showed that the value of the potential at the medium can be written in a very compact form, and this is very useful, as I'll explain in a moment. And the only difference between the 5 vacua is that the value of this lambda p, which can be A, B, C, C prime, and D, is different, depends on the parameters of the potential, but you have an explicit expression for each of the vacua of the potential. Now, for the symmetric case, we also derived conditions for each of the vacuum to be a local minimum. In fact, this was not completely correct in the literature. Then we correct some misprints and mistakes in the literature. And the next step was we wanted to give a procedure to ascertain if the potential is the global minimum along the neutral directions. And this use some results that Ivanov have derived before for the neutral directions. The problem is that no such result exists for the charge directions. Therefore, we derived, again, sufficient conditions to be bounded from below along these charge directions, and the procedure is very much similar to what I've explained before, and I want to go through it at the moment. Now, the last topic is related to what I just told you, that you have only these 5 vacua, and Jean-Paul Silva and collaborators, just after Ivanov discovered these 5 vacua, they have shown that it's not possible to have a fit of the quark mass matrices with non-degenerate and non-zero quark masses, which means that this symmetric A4 model was not good for describing the quark mass matrices. And this might appear as a surprise for some people, because the number of parameters in the observables is exactly the same. But despite you have as many parameters as observables, due to the structure of A4, it was not possible to have a fit. It was conjectured and shown by us later that a good fit could be possible if you could move away from those 5 vacua. And how could you move away from those? Well, just by moving away from the symmetric case. And then we investigate the possibility of softly breaking A4 symmetry just to move away from the VEPs. And for this, you add to the symmetric potential some quadratic terms when we took the most general emission matrix. And with that, we tried to see if it was possible just to bypass this theorem or conclusion from this.
I have a question.
Yes.
order to generate this quark masses, you're not considering at all radiative corrections or seesaw mechanisms or anything like that. It's just
No. It's just tree level. Okay.
just Yukawa coupling. That's it.
Yeah, just Yukawa coupling. Yes. I'll show you in a moment what I mean. Okay. In fact, let's look at the Yukawa Lagrange. And then we are in A4. Then you have to assign the Higgs doublets and the quarks to the representations of A4. We put the Higgs doublets in the tree, and as the left-handed the quark doublets. As for the right-handed, they are both the hypercharged -1/3 and hypercharged 2/3. They are singlets, and you assign them in this way. I mean, the first family is to the 1, the second family to 1 prime, and the third to 1 double prime, the 3 singlet representations of A4. And the A4 transformations on the fields, they preserve the potential. You can check that, but we define them in this way. And with this definition of the transformation properties, one can check that this Yukawa Lagrangian is invariant, is A4 invariant. And in these expressions, we have put some constants that afterwards you redefine, essentially taking the absolute value and the phase, because this can be complex numbers. And also the phi tilde is the usual definition, the complex conjugate multiplied by I sigma 2, the Pauli matrix. And these A, B, C, A prime, B, C, C prime are real and positive. It turns out that these phases are going to disappear. That's why this convention is nice. Now, with this, once you put the vacuum expectation value from the field, you can write the down quark matrices in this form. And this can be written as a product of simpler matrices. D is for diagonal, and W is this A4 matrix that depends on this omega, the e to the I 2 pi over 3. And dV is the diagonal matrix for the VEVs, dA for these entries, and d alpha for the phases. Don't forget that the VI are complex. Then you have that's why you have to be careful with that. Now, if you do this is for the down quark matrix, but of course from here you also get the up type matrix, and you get exactly the same form. With this transformation, you go from non-prime to prime parameters, but for the VEVs you have to take the complex conjugate. And with that, now these phases disappear because of this condition. Once you instead of looking at the down and up quark matrices, you instead look at these emission matrices, which are constructed from the quark mass matrix. Of course, the eigenvalues of these matrices are the square masses of the quarks, down and up. And because this is nicer, because, for instance, these angles alpha disappear from this formulation because of this condition. And this is just the diagonal matrices, and you get you can write this H down and H up in this form, where this matrix S is just given by this product, and it can be written in this term. We found it more convenient to write in this form, where these sigmas and Z and phi and phi's are related to the previous parameters A, B, and C. Then instead of using A, B, and C, we use this sigma D. For down quarks, we use sigma D, ZD, which is a real number, positive, and the phase. And this is more convenient to do the fitting than to use the original ABC. But of course, the number is the same. Now, if you go to the up case, you just move into you put everything primed, and do not forget to take the complex conjugate for the VEVs. There, it's different, and that's it. Then the idea is that you are going to find these parameters by fitting the eigenvalues of the matrix HD and H up to the known values of the square of the quark masses. But of course, you don't want just to do that. You want to do more than that, because you want also to fit for the CKM matrix. And for that, you use the result, old result by Branco and Lavora. Then they have shown that the absolute values of the CKM matrix can be obtained by calculating the traces of appropriate powers of H, U, and HD by these expressions, where these U are just the absolute value square of the CKM matrix. And as this matrix is unitary, you need only 4 of them. And for instance, you can choose these combinations just to take 4 of these values, which, as these expressions are written, are linearly on the square of the CKM matrices. You can invert these expressions, like I'm showing here. You can invert these expressions, and for instance, choose 4 of them. For instance, U11, 21, 13, and 23. We found more convenient to work with these 4 because they are better known. Then you have an expression for this absolute square of the CKM matrix written in terms of the masses of the quarks. The determinant also only depends on the masses, and these A1, A21, A13, and A2 are complicated expressions that I'm not writing here. They depend on the masses, but also on these Lij, which are obtained by just taking the traces of these matrices, which depend on our parameters. Then with this, we have a setup where you have the 10 quantities that you want, the quark masses, which are obtained by getting the eigenvalues of these HD and H up, and the CKM, which are obtained by solving these equations. Then we make a fitting procedure to determine the parameters that give the best fit. And our parameters, as I told you, they are 10, exactly the same number of the parameters for the quark, 6 quark masses and 4 CKM parameters. And we have beta 1 and beta 2. I mean, and row 2 and row 3 are the phases of the VEVs. And these are the 3 parameters for the up quarks and the 3 parameters for the down quarks, those that enter in this H up and H down matrix. And once you have this, you get an excellent fit, even for the Jalskog determined, you get something very close to the experimental value. Now, well, this is very good, but what is the problem? Well, the problem is that the VEVs that we get in this way are very, very far away from those 5 vacua that we have in the A4 symmetric case. In fact, they have some kind of hierarchy, and of course, the hierarchy comes from the hierarchy of the quark masses, and these are the values that we get. Now, what remains to be checked? It remains to be checked that we can, using a A4 softly broken model, that we can make it compatible with these values for the VEVs. And that's what we want to do. For this, what we have to do, we have to implement the code with the model. And again, we, as before, we require unitarity, bound from below, S to U. You also require that all the square masses are positive definite, means it's a local minimum. And you check that when you diagonalize the H up and H down, that you get 0, which means that you get the correct neutral and charge Goldstone. then you require that you have a scalar with a mass of 125. Of course, as in this process, we are doing it in a completely opposite way, as I was explaining before in the Z3 or Z2 cross Z2, because we are not inputting the masses, but we are getting the masses through diagonalization. We are not sure when you diagonalize the mass matrix for the scalars that you get the 125. Then of course we have to require that, and of course it's you have to do some kind of tuning to get to this, but it's possible. And of course, you also want to look at the constraints from LHC. Here we just look at the kappa V. I mean the ratio of the coupling to the gauge bosons in our model with relation to with the standard model, and this is now known to be close to 1 in a very narrow range, and you also require that. And finally, the last point is that you also check that for each point in perimeter space, the minimum was not only local, but also global. And that took a while because this numerical method is slow, but to verify that all points that you use in our plots, they are also global minimum. Now, just a couple of plots just to show one thing that we found in this by doing this is that there is a strong correlation among various masses of the scalars. Again, in groups of 2, you have 2 scalars and one of the charge Higgs, and the other 2 scalars and the other charge Higgs. They are related. For instance, here I'm showing the 3 and 4, and this happens even before applying cuts meaning all the constraints. They are already, which means that therefore is already making these correlations, and once you apply all the constraints, the correlations become much stronger. This is for the 3 and the scale. You could do similar plots for the others. Okay, and this brings me to the conclusions. Now we have implemented sufficient bound from below conditions for a large class of 3 HDM. This is important because necessary and sufficient conditions are only known for a couple of cases, and these methods can be generalized to other problems. The 3 HDM models are unique because the new type Z coupling to fermions needs at least 3 doublets. And if you have 4 doublets, there is not much difference because you have already a simpler case, the 3 HDM, where you have this Z type. We discussed the possibility of distinguish the Z2 cross Z2 and Z3 implementations of this type Z. We found that the good observable is the kappa H, the ratio of the triple X coupling in the model to the standard model. It tends to be smaller than 1, and it can be lower in Z2 cross Z2 case, and eventually, if this is the case, can point to this model. Of course, if the value it's lower than 1, but let's say 0.9, then as you have seen in the plots, there is no possibility of distinguish between the 2 models, but that's, of course, that's a possibility. Now, finally, we discussed the vacua of the A4 symmetric model. We found new sufficient bounded from below conditions along the charge bracket directions, which are important because the necessary and sufficient conditions along these directions are not known. An excellent fit for the quark mass matrix was obtained for the softly broken B4 model. We were able to show that the obtained vacua structure is compatible with the scalar potential. And finally, we verified that any solution for a good point in perimeter space is also a global minimum, and this is non-trivial. Thank you.
Thank you very much, Professor Jorge, for the very nice and complete seminar. question from the audience?
Yes, I have a couple of questions.
Yes,
Yeah.
go
First about the alignment limit. I mean, in this case, how do you know that these extra scalars and all that are not going to take the couplings of the usual Higgs and properties of the usual Higgs away from the standard model properties?
Well, if I'm in this alignment limit, then the potential is very simple, and the couplings of the standard model X are, I mean, the lowest scalar is essentially the standard model X. Then essentially passes all the constraints from LHC and from unitarity and bound from below. And for the other scalars, they essentially the masses will be kind of dictated by the soft terms, and you can then essentially you can have you can respect the STU constraints easily. Then that's what, at least what we found numerically. I don't know if that answers your question.
Okay, I have another question about the Yukawas that you mentioned.
Yes.
Obviously, you have to use some vacuum expectation value to give masses.
Yeah.
Is that the usual
You-
vacuum expectation value? I mean, do you have one doublet that in which to have a non-trivial vacuum expectation value?
Are you talking about A4?
About the Yukawas, I mean, you
Yeah,
give
but
masses.
but about the type Z or
How do you
about
give masses to the
yeah
fractions through Yukawas?
yeah
What's the vacuum expectation value that you're using?
no, I'm using each each doublet as a vacuum expectation value, V1, V2, and V3.
So only one doublet, only
Yeah, they all have vacuum expectation value. For instance, if let me show one thing. If you go to the beginning, where we had this discussion about the different types. I mean, in type Z, you have phi1 couplings to the charged leptons, phi2 couplings to the down quarks, and phi3 to the up quarks. Then if you want to give masses to this type of fermions, you have to give vacuum expectation values to all fields.
Wonderful.
Okay.
Okay, thanks.
Okay. And also in A4, when you write your Lagrangian, you have to give vevs here, and you have V1, V2, and V3 that appear in these expressions. The difference between the A4 case and the type Z that I was showing before is that here the vevs are complex in general, although there although it will also be possible to have spontaneous breaking of CP, we did not consider that. Here the vevs are complex, and that comes because of A4. A4 has this complex structure, and the solutions will give complex vevs. Okay.
More question from the audience? Questions? I had one question. In this model with the apply for the quark sector,
Yes.
what about the constraints arising, for example, for later quark decays? Because we will have 3 Higgs doublets, so there will be flavor change in neutral coordinate as well as Mason oscillation constraints.
Yeah, no, that you are right. That's something we have to worry, and we did not yet. I mean, that's I mean, you just wanted to what you just did was just to solve this problem. I mean, it is possible or not to fit the quark mass matrix, but of course we have to address those problems, which we did
So
not.
maybe you could put extra constraints, or maybe this later decay
well,
will be.
Eventually, if you are unlucky, it could kill the model. But we have not studied it, and I cannot answer that.
And for the electron sector, you seen on a type 1 season implementation? Or the
Yeah.
model is mostly focused for the quark sector?
Yeah, the model is just for the quark sector. For the lepton sector is a bit more difficult because we cannot apply. Well, we tried, but we cannot apply the same assignments for the leptons. We could not find a good fit for also for the leptons. Then you have to complicate the theory a little bit. The easiest way out is to add to the theory an extra singlet, but we have not. I mean, this was suggested by Ernest Ma because he kind of also studied this type of models, not in the quark sector but in the lepton sector. Then he had the opposite problem. He was looking at the lepton sector and that had problems with the quark sectors. And what he suggested was that you could enlarge the theory. There are several ways of enlarging, but the minimal way just will be just to put an extra Higgs singlet. And of course, we have to look at the scalar potential, and we have to cross-check that everything is correct. We have not done that yet.
I was wondering in this model with quarks, why the other possibility, for example, of having the right-handed quarks, right-handed adundante quarks unifying to an A4 triplet, and the left-handed quark unifying to assigned as different A4 singlet. Would that case work with the without adding the breaking term?
You are suggesting that you make another representation?
No, I was asking if the other possibility, for example, of considering left-handed quarks as a singlets, one prime and one prime on the A4, and the right-handed quark unified into a triplet, will the one of the bed configuration of A4 will work? Have you explored that possibility?
Well, we have tried a little bit that, but not for the leptons, not for the quarks, and somehow it didn't work. But yeah, but for the quarks, we have just used these kind of assignments, which were done before by several people. And it's not new, this kind of assignment for A4. For the lepton, trying to solve the leptons, we tried to use other representations. Well, if you just copy this for leptons, does not work. Now, then we tried to use other assignments, but we were not successful up to the moment.
Thank you.
Okay.
More questions from the audience?
I'm stopping share. Okay.
If there are no more questions, we send the speaker for the very nice and complete talk. And we meet at the next seminar. Thank you very much, Professor Jorge. Thank you very much for the very nice talk.
Thank you for listening to me, and it was a pleasure. And we perhaps can do it at some other time again. Okay. Thank you very much. Bye.
You're welcome. Thanks to you.
Okay.
Bye.
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 Thank you, George.
Ciao.
Thank you.
Until next time.
Bye-bye.
Bye.